All right, so in this next half lecture, I want to do one more example of a induction proof. And then I want to move, so here we're still hanging out in 5.1, which is induction. So I want to do one more example here, and then I want to move on to 5.3, which is strong induction. We won't be spending too much time with strong induction, but at least one of these half lectures and maybe a little bit more time. And one nice thing that we'll get out of strong induction is we will get a proof of at least a chunk of the fundamental theorem of arithmetic, which I have punted on so far. But first I want to do one more fun example, just so that you see kind of a large variety of problems that we solve by induction, and so that you see a lot of the proofs, so you kind of get the hang of the steps. Okay, so the example that I want to do is as follows. So let's prove that n squared minus 1 is divisible by 8 whenever n is an odd positive integer. Okay, so one thing that isn't mentioned in the steps, but that I've been doing a little bit and that I want to bring out here is that when you're doing an induction problem, it's often convenient to work out a couple of the small cases, maybe more than just the base case, and get a sense for kind of why this thing that you're being asked to prove is true. So let's do a couple examples here. So here, the statement P of n is, what I really want to do is I want to change my variables. So instead of saying that n is some odd positive integer, what I want to make is I want to make a statement P of 2k plus 1 for k in z and k greater than or equal to 0, right? This is just another way of getting a hang of all of the odd positive integers. I can write them all of this form. They're all 2k plus 1 for k and z, and k is greater than or equal to 0. Okay? So let's look at P0, which is the statement that 8 divides 1 squared minus 1, right? Maybe I'll write 2 times 0 plus 1 squared minus 1. But 2 times 0 plus 1 is 1. 1 squared is 1, and 1 minus 1 is 0. And indeed, 8 divides 0, since 0 is equal to 8 times 0. So by divisibility, we can see that 8 indeed does divide this term. Why don't we do P1, just to kind of see what's going on, and maybe P2. It's not a bad idea. P1 is the statement that 8 divides 2 times 1 plus 1 squared minus 1. 2 times 1 plus 1, this is 3. So this is 3 squared minus 1 is equal to 8. And indeed, 8 divides 8. So P2 is also true, or P1 is also true. P2 is 8 divides, now here I'm going to have 2 times 2 plus 1 squared minus 1. So this is 5 squared minus 1, which is 24. And indeed, 8 divides 24. So we've kind of checked the first couple steps and seen, yeah, indeed, it seems that this proposition is true. And notice also that I changed the way that I was indexing things. Instead of letting n range over all positive integers, I changed so that I'm dealing with k. And now I'm only considering the statements p of 2k plus 1 for all k. Okay. So proof by induction. Show p of 2k plus 1 is true for all k in z greater than or equal to 0. This is what we're trying to show. Okay, the base case is one that we've already checked. P0 is true since 8 divides 0, essentially. Okay, so the base case is done. Now we want to perform, base case. Base case, P0 is true since 8 divides 0. Inductive step. So the inductive step here is for an arbitrary k greater than or equal to 0, p of 2k plus 1 is true. This is the inductive hypothesis. And so p of 2k plus 1 is the statement that 8 divides 2k plus 1 squared minus 1. So when I use the inductive hypothesis, I will be using this fact. 8 divides this number. This is the worst board to start on. Okay. Okay, I'll rewrite things here. So p 2k plus 1 is 8 divides 2k plus 1 squared minus 1. In the inductive step, I want to try to understand what's going on in k plus 1. So what I should now try to think about is p of 2k plus 1, which is really the same thing as p of 2k plus 3. All that I'm saying is if I know something for the odd positive integer 2k plus 1, then the next thing that I need to check is the odd positive integer, which is given by that same 2k, but plus 3 instead. If 2k plus 1 is 5, then the next thing that I want to check is the property for 7. Okay? So let me write out a piece of the, let me write out a term of p 2k plus 3. So what I need to check is, does 8 divide 2k plus 3 squared minus 1? Okay? And I'm going to try to verify this. If I can verify that 8 divides 2k plus 3 squared minus 1, then I have checked that p of 2k plus 1 implies p of 2k plus 3. That is, knowing it for the previous odd integer implies it for the next odd integer. Does 8 divide 2k plus 3 squared minus 1? So let's compute. Let's write 2k plus 3 as 2k plus 1 plus 2 squared minus 1. Well, this term, I'm gonna treat this as one piece, and I'm gonna treat this as the other piece, and I'm going to FOIL out. So this thing is equal to 2k plus 1 squared plus 4 times 2k plus 1 plus 4, all minus 1. Right? I'm treating this as a and this as b, so I get a squared plus 2a times b plus b squared, and then I remember the minus 1. Okay? So by the inductive hypothesis, the thing is I should be recognizing this chunk, this 2k plus 1 squared minus 1. By the inductive hypothesis, eight divides 2k plus 1 squared minus 1. Okay, so I know that it divides this chunk. Let me examine what's left over. Moreover, 8 divides this thing, because 4 times 2k plus 1 plus 4. Moreover, 8 divides this term, since 8 divides, I'm just going to factor out 8k plus 8. Right? I'm going to get an 8k plus 4, and then I add 4 again. So this term is really 8k plus 8. And since 8 divides 8k and 8 divides 8, 8 must divide their sum. So what I have shown is that this term, which I was interested in, can be broken up into two pieces. 8 divides this piece by the inductive hypothesis. 8 divides this piece by calculation. And if 8 divides this number A and 8 divides this number B, then 8 divides their sum. By rules of divisibility, 8 divides 2k plus 1 squared minus 1 plus 8k plus 8. Thus, the inductive step is proven. And by induction, eight divides, what is it in the end? N squared minus 1 for all odd positive integers n. Okay, so some things to comment on here. This proof is a little outside the ordinary mold of these induction proofs that we've been doing for the following two reasons. First of all, we're not proving a statement for all integers. We're proving it for all positive integers, and then I can relate that back to all integers by doing this trick of writing all positive odd integers as 2k plus 1 for some k. So notice that I'm never considering p of an even number. I'm only considering p of odd numbers. But I can still use induction because I can still show that if I have the statement p of 2k plus 1, then I have the statement p of 2k plus 3. And all odd numbers are of this shape. The second thing is that I didn't use my hypothesis in an equality. Like I didn't swap out in some equation the expression for p of 2k plus 1. The place where I use the inductive hypothesis is to say that 8 divides some piece of this expression. So it's a little more involved in that sense as well. Okay. So that's a nice problem to prove by induction. Okay. Okay, so the next thing that I want to do is change gears. So I've now done a plethora of examples of induction. So I've done a bunch of examples of induction, and now I want to move to the next section, which we will cover, which will be 5.3. And this is going to be strong induction. So this is a related technique. It's actually logically equivalent to induction, but there are a certain number of problems that can be solved pretty easily with strong induction that are harder to prove with just regular induction. Okay, so for some comparison, the logical structure of induction, so induction, logical structure here goes, if you have the statement P of 1, and you have the statement that for all k, P of k implies P of k plus 1, then you produce the statement for all n greater than or equal to 0, or I'll just say for all n, but here n is understood to be a positive integer, P of n. This is the logical structure. And in the metaphor of the ladder that I discussed last time, the P of 1 statement is saying you can get on the ladder, and then the second statement is saying whenever you're at one rung of the ladder, you know how to move from that one rung to the next rung up. And then this conclusion is then saying you can climb up to an arbitrary rung on the ladder. Strong induction, on the other hand, looks as follows. You start off once again with the base case. So say P1 is still the base case. But now, instead of just relying on information from the previous term, that is, instead of just relying on k to get to k plus 1, we now assume a whole bunch of statements. Next, we assume for all k, P of 1 and P of 2 and all the way up to P of k implies P of k plus 1. So essentially, the difference here is that anytime that we were doing induction, we were always able to relate whatever was going on with P of k plus 1 back down to something involving P of k. But there are plenty of cases where what you're working with P of k plus 1 isn't just related to P of k, but maybe it's related to P of k minus 4 or P of k minus 7, or maybe it's related to several terms. And so what you want to do is you want to assume all of the lower terms and see if altogether those imply P of k plus 1. And then if you have this proposition and this proposition, you can conclude that for all n positive integers, P of n. Okay? So on the face of it, strong induction and induction seem like very different proof techniques, mainly because strong induction assumes so much more. In the inductive hypothesis for induction, I only assume P of k. In the inductive hypothesis for strong induction, I will assume P of k and P of k minus 1 and P of k minus 2, so on and so forth, all the way down to P1. So I'm assuming a much larger pool of statements when I try to prove P of k plus 1. It turns out that the three methods, induction, strong induction, and the well-ordering principle, these three things are equivalent. So last time what I showed was that if you have the well-ordering principle for the integers, which we in this class are assuming, then you can get induction. It is also true that if you use the well-ordering principle, you can prove that strong induction follows. Similarly, induction alone can also actually prove that strong induction works, and vice versa. So if you take any one of these three, you can recover the other two. So logically speaking, induction or strong induction isn't any stronger than induction, and vice versa. It's just that they work a little differently in problems. And yeah, for the ladder metaphor, here, this is saying P1 gets you on the ladder, and then this step says, if you are on any of the, let's see, here it says, if you can reach all of the first k rungs, then you can reach the k plus first rung of the ladder. Okay. As a first beautiful application, an example, we are going to prove a part of the fundamental theorem of arithmetic. So prove that any positive integer k greater than or equal to 2 has a decomposition or also called a factorization into a product of primes. Okay? So we're going to prove this by strong induction. And in terms of the steps, a strong induction proof looks very similar to an induction proof. The only difference is what you assume in the inductive hypothesis. So we're going to start with a base case. And what is our base case? Oh, shoot. Okay, I hope that hasn't been going on for very long. Okay, so what we need to do next is we need to prove the base case. So prove that any positive integer k greater than or equal to 2 has a decomposition into a product of primes. And we're going to prove by strong induction. The first thing that we have to do is we have to set up a base case. The base case here should definitely be 2. So I want to show that 2 can be written as a product of primes, and that's pretty quick. Base case P of 2. P of 2 is true since 2 equals 2 is a decomposition into primes. Okay, so the base case is pretty straightforward. Next, we need to do the inductive step. The inductive step is what we want to show is we want to assume, we will be assuming that P of k, so for an arbitrary k, P of I is true for 2 less than or equal to I less than or equal to k. this is what I'm going to be assuming in the inductive hypothesis. So what this is saying is fix some integer k and assume that every number equal to k and less than k has a prime factorization. That's what I'm assuming here. If I say take k to be 100, then this assumption is every number between 2 and 100, every integer between 2 and 100, has a factorization into prime numbers. And what I want to show is p of k plus 1, because I want to show k plus 1 has a decomposition into prime numbers. So we examine k plus 1. Now, there are two cases for k plus 1. Case 1, k plus 1 is prime. Right? It's possible that k plus 1 is a prime number. If k is 100, then indeed 101 is a prime number. If k plus 1 is prime, then we are done. Because it can be written as a product of primes, namely it's just itself. In the second case, k plus 1 is composite. And composite means, so k plus 1 is composite, which means that I can write it as a product of integers a and b, such that a and b are non-trivial. So in particular, neither a and b are 1, and neither a and b are k plus 1. So k plus 1 is equal to a times b, where a and b are not equal to 1 or k plus 1. And they're positive integers. Now, since a and b are neither 1 nor k plus 1 and they're positive integers, a lies inside this interval between 2 and k. A is inside, 2 is less than or equal to a is less than or equal to k, and also 2 is less than or equal to b is less than or equal to k. Right? Now, by the inductive hypothesis, by IH, I know that A has a prime factorization and B has a prime factorization, because that's what we are assuming in the inductive step. We're assuming that for every integer in between 2 and k, they can be written as a product of primes. So I'm going to write A is equal to P I1 A1 all the way up to P I K A K. This is just saying A can be written as some product of primes, and B also is Pj1 B1 all the way through Pjl Bl. Also, B can be written as some product of primes. And then, I'm out of space. So now, then k plus 1 is equal to A times B, which is equal to P I1 A1 all the way up to P I K A K times P J1 B1 all the way up to P JL BL. So we have written k plus 1 as some product of primes. Thus, P of k plus 1 is true. So if I assume that I have prime factorizations for all the integers between 2 and k inclusive, then I have a prime factorization of k plus 1. Thus, so this completes the inductive step. Thus, by induction, every positive integer has a prime factorization. Except 1, right? 1 doesn't have a prime factorization. But every positive integer greater than 1 has a prime factorization. Okay. So this proves half of the fundamental theorem of arithmetic. The other half is that such a prime decomposition is unique. We didn't prove that explicitly, but you have the tools to prove that yourselves if you start working with divisibility. And it's in the book in section 4.3 near the end, so I recommend that you go through that. Okay, let's do one more example of a proof by strong induction. This is also a problem that can be solved by regular induction, but it's good to see both examples. So, we have the following fun problem. Show that any postage of value 12 or greater, 12 cents or greater, can be achieved using 4 cents and 5 cent postage. So this is saying that if you show up to the post office with an infinite number of 4 cent stamps and 5 cent stamps, and then the postmaster tells you that it costs any dollar or cent amount greater than 12 cents, you can always fill up your postcard with, I don't know, a bajillion stamps and get the right number. This can be proven both by induction or by strong induction. Oh, an important note, the previous proof about the fundamental theorem of arithmetic, it is not at all clear how to prove that using standard induction. Because if k plus 1 is not prime, and it has some factorization, then we were able to write, you know, it's a product of A and B, but those A and B are almost certainly not involved or not related to k, right? It's almost never that k is a factor of k plus 1. So proving that previous proposition by induction, I don't see a way to go about it. Whereas this proposition can be proven either by induction or by strong induction. And also actually in other ways. So we're going to do something interesting here. We're going to take a larger number of base cases than usual. So base cases. Well, the first thing that I want to do is I want to show that I can do this for P12, P13, P14, and P15. Well, 12 is just equal to 4 times 3. So I can write 12 cents as 3 4-cent stamps. 13 is equal to 5 plus 2 times 3. 6 plus 5 is indeed, no, wait, 2 times 4. 2 4-cent stamps and a 5-cent stamp. 14 is equal to 2 5-cent stamps plus a 4-cent stamp, and 15 is equal to 3 5-cent stamps. So in this base case, what I've shown is I can solve this problem when the postmaster asks for 12 cents, 13 cents, 14 cents, or 15 cents. And it's fine to have more base cases than just one. It's not an error or an issue. So these are the base cases. I can do it for these couple. Next, for the inductive step. What I'm going to assume, or what I'm going to say, yes, we will assume that for k greater than or equal to 15, that P of k, so that for all I, such that 12 is less than or equal to I is less than or equal to k, P of k holds. So what I'm saying here is pick some arbitrary k bigger than 15. I don't need to go lower than 15 because I checked all of those. I know it's true for all of these. So take some k greater than or equal to 15 and assume that I can, for any of those numbers, find some combination of 4-cent stamps and 5-cent stamps that do the trick. And now what I want to show is that I can assemble some collection of stamps for k, pi, for k plus 1. Now must show P of k plus 1 holds. E.g., k plus 1 can be written as n1 times 4 plus n2 times 5, right? I'm just trying to find positive integers such that a certain number of 4-cent stamps plus another certain number of 5-cent stamps will get me k plus 1. So I want to show that this holds based on this inductive hypothesis. So now, given k plus 1, examine k plus 1 minus 4, which is equal to k minus 3. Since k is greater than or equal to 15, 12 is less than or equal to k minus 3, which is less than or equal to k. Thus, k minus 3, P of k minus 3 is true by the inductive hypothesis. Right? My inductive hypothesis is that any of these numbers in between here, I can find the right postage using 4 and 5-cent stamps. Now, if I take k plus 1 big enough, I know that if I take 4 cents off of k plus 1, it'll land me into the region where I know I can get the right postage. Then, by adding a 4-cent stamp, to the collection giving P of k minus 3, I get a collection, I get stamps of 4 cents and 5 cents, adding up to k plus 1. Okay? And then just to be very thorough, I would say this completes the inductive step. This completes the inductive step. Oh, sorry, Brian, I'm working. This completes the inductive step. So by induction, any postage 12 cents or higher can be gotten using 4 cents and 5 cent stamps. Okay, one more comment that I want to make about this is that in the regular induction, what you did is you related the P of k plus 1 back down to the P of k. That was kind of the technique that we used for regular induction. Here, in this version of strong induction that I did for this particular problem, it succeeded because I could always relate the P of k back down 4 steps back. Instead of just moving 1 step back to k, I moved 4 steps back all the way down to k minus 3. But then once I know something about P of k minus 3, I can prove something about k plus 1, because it's 4 cents away. So once I have a collection that does the trick for P of k minus 3, I just add in a 4 cent stamp and I get all the way up. So hopefully this shows one of the ways in which strong induction is used. Even if you can't relate P of k plus 1 to the statement P of k, maybe you can relate it to some statements further back. And strong induction tells you that still makes a valid argument, and you can still prove these sorts of statements in that fashion.